Okay, now I'm going to show you folks, after we went through the process in the last video of what the techniques are to solve these statics problem. Remember that for statics, you want it to be that all of the forces add up to 0. And the only way you can do that by vector addition is if f sub x equals 0 and the way you have it now, r sub x equals 0 and r sub y equals 0. Everything has to add up to 0 in order for there to be static equilibrium. We talked about the fact that for the techniques, you're going to make a drawing. You're going to choose one part of the drawing and draw it separately. We're not always going to do that, but that's an option to do. Number 3, you're going to draw the arrows to represent the forces. Number 4, you're going to superimpose an xy axis. Number 5, you write the r sub x and r sub y equations, making sure that they're equal to 0. And then number 6, you solve for the unknown. So let me just talk you through this problem to start with. So the first thing I'm going to do, and we're on capital letter B number 1, first thing I'm going to do is I'm going to actually make my drawing. And I'm going to draw a hanging plant. So here's my hanging plant, and it's a fern. We're going to have it be nice and pretty that way. Draw a fern or draw something that is a hanging plant on your notes. And again, drawings are important. It's fun if you can make them look good, but if that's just too tedious for you or you just really don't care that much, it's all right just to make it a box. But I have wires, and I'm going to make the wires a different color just because I really want them to be visible. So I have wires coming up here, and then coming up at the top, and right here is where and at the very, very top is where it attaches to the ceiling. So here's my wire, and it attaches up at the top. Okay, that's my drawing. That's the first thing I do. Now, I'm choosing a part of it, and I guess if I want to really deal with it, the important piece is really right here where it attaches. But the whole drawing is kind of important. So I'm going to draw the arrows. I'm on number 3 now. Draw arrows to represent all forces acting on the object. So I'm going to ask myself, what are the forces at play here? And in Chapter 4, we're really going to identify the forces very specifically. But right now I'm going to tell you the forces are that I have the weight going down and the tension on the wire, and I'm going to call that T, the tension on the wire going up. And I've actually represented them symbolically with a T and a W, so I'm good. Next thing I'm going to do is I'm going to superimpose an XY axis, and I'm just going to pick a different color so that I can see the XY axis. So I'm going to superimpose it. Obviously, the x-axis is going to go over my forces. It doesn't really matter where I put the y-axis because I don't have any vectors that are in any way, shape, or form horizontal. So I can put it anywhere on my XY axis. And now I think I'm just going to use black with this. The last thing I'm going to do then is write the 2 equations for the first condition. So it looks like this. The first condition is r sub x, but I'm going to start using a different designation for r sub x. I'm going to call it sigma f sub x. It's the same thing as r sub x, but sigma means sum. I'm going to add up or find the sum of all of the x components. You'll notice that the 2 x components are weight and tension. By the way, you were given at the beginning of this, which I failed to tell you, I apologize. The weight for this is actually 90 newtons. So what I'm trying to find in this is what is the tension on the wire. Now it should be kind of obvious that if it's pulling down by 90 newtons, then in order to keep it from falling, it has to be pulled up by 90 newtons. But let's let the math take care of that so we can just see the process. I didn't want a hard problem to start with to show you the process. I just wanted to give you an example where you saw what to do before worrying about the, wait, where did all those numbers come from? All right, so I have my 2 components, so it's going to be W sub x plus T sub x is equal to 0. So I know that W sub x is W, I can actually do what the weight is. I'm sorry, let's go ahead and put that in. My weight is 90 cosine of 90. Oh wait, I know that that's equal to 0 plus T sub x, I don't know what x is, I do, but we're going to pretend that I don't know, is equal to 0. So what is t sub x equal to? T sub x is equal to 0. Notice that I had to set this, well, that was not good. Notice that I had to set this equal to 0. Wow, I have no idea where I am right now. Give me a second. I don't know what happened. There we go. Oh, I see. There's up at the very top, there's a chapter 1. All right, notice that I set this equal to 0. That's the first condition of equilibrium. Sigma f sub x is equal to blah, 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 is equal to 0 every time I set it equal to 0. That means t sub x now is equal to 0. Sigma f sub y is equal to w sub y, but I'm going to call it negative because notice that it is in the negative y direction. So it's negative w sub y plus t sub y is equal to, again, 0. My first condition of equilibrium says that sigma f sub x and sigma f sub y both have to be set equal to 0. And I'm going to fill in what I know. So a negative 90, I'm sorry, now it's sine. Sorry about that. Negative 90 sine of 90 plus t sub y is equal to 0. This then is going to be negative 90 plus t sub y, that's a t, is equal to 0. So t sub y is equal to 90 newtons. I'm going to throw it into my r because what I know now is I know the x component of my unknown tension. I know the y component of my unknown tension. If I know x and I know y, then in order to find the actual tension, I'm going to have to use a squared plus b squared equals c squared. So r, my resultant, is equal to the square root of sigma f sub x squared. Notice that it's the same equation, I'm just using sigma f sub x instead of r sub x, plus sigma f sub y squared is equal to the square root of 0 squared plus 90 squared, which is equal to 90. I kind of predicted that. It's 90 newtons. Now, this one's a little bit of a problem trying to find theta. You're going to have to actually know your math for this. It's the only time this ever comes up. Theta is equal to the inverse tangent of the absolute value of r sub y, which is 90, over, and this actually pains me to write it down, 0. That's not a thing. This is undefined. And those of you that know trig, you will know that theta, or that tangent rather, is undefined at 90 degrees. So what I have is 90 newtons, 90 degrees, and because this is positive, t sub y is positive, it's going to be north. All right, let's just recap this very quickly. I have my drawing. I put in my different forces that were acting on the drawing, the weight, which was 90 newtons, and the tension pulling it up. Put in an XY axis so that I knew what angles it was at, and then just went ahead and put it in my sigma f sub x equation where it's equal to 0. Y is equal to 0. I have my x component and my y component, and just like we did in chapter 1, I take the x and the y and I put it in this equation. I take the x and the y and I put it in this equation. The only thing that's bizarre about this is when I have a 0 in the denominator, never will my calculator put up with that. So I have to just know that for 90 degrees, tangent is undefined. And again, those of you that are good at the math piece of it, when by undefined it actually means that at 90 degrees it approaches, but it never quite gets 90 degrees. And so it's undefined. There's no real answer for it at 90 degrees. All right, now that takes care of that particular problem. I'd like to go ahead and do one more problem with you, maybe 2 problems with you to show you what it looks like. So the next thing I want you to do is number 7 in the class notes, if you're following along, And number 7 is 3 people pull on ropes attached to a ring as shown. What is the magnitude and direction of F sub 3? So what it's saying is if I want to keep this at equilibrium, if I want the ring in the center not to move, what does the force on F sub 3 have to be? So what we're going to do is, first of all, do the drawing. I think you have the drawing there. If you don't, then it's actually F sub 1 that I'm looking for. I'm sorry, not F sub 3. So here's my drawing. I have my XY axis. I have a ring in the center. And I have F sub 2 going off completely west at 200 newtons. That's F sub 2. That's F sub 3. F sub 2 is going straight down, and this is 150 newtons. Now, my guess is that F sub 3 is going to have to be somewhere in this direction, but I don't know what it is. I'm going to pretend I have zero idea where and how big F sub 1 is. This is F sub 2, this is F sub 1. All right, so this is how we set it up. I've got my drawing, I've got my forces put in, I've got my XY axis. Now I'm going to do my sigma F sub x. I have 3 forces. One is F sub 1x. I have no idea what it is. I don't know what quadrant it's in. I don't know the magnitude of it. There actually is no drawing for it. I'm just kind of roughing that in, but it's not there. So I have no idea what it is. I'm going to let the math tell me what it is. But I do know that F sub 2x is going to go down, and I know eventually that's just going to cancel out because there's no horizontalness to a vertical vector. Minus F sub 3x, ask yourself very quickly, why negative? It's because it's on the negative x-axis. And what does the whole thing equal? Always it equals to 0. And I will expect on all of your worksheets to see equals 0. Let's plug in what we know. We know then F sub 1x, and that's all we know. We don't know sines, we don't know what theta is, we know nothing. Minus, I'll do plus 150 cosine of 90, and I know that the cosine of 90 is 0, minus 200 cosine of 0 is equal to 0. So this ends up being 200, so F sub 1x minus 200 is equal to 0, so when I move it over, it's equal to 200 newtons. Now let's do the sigma F sub y. Sigma F sub y is equal to F sub 1y. And again, I don't know if it's positive or negative. Minus F sub 2y, I do know that because it was drawn for me and it's going straight down, plus F sub 3y, which is going to cancel out because it's on the x-axis, is equal to, they always add up to 0. So I'm going to plug in the numbers that I know, and I'm going to leave what I don't know, F sub 1y, I have no idea what it is, minus 200, do I have those backwards? I have those backwards, I'm sorry. This one is positive, I don't care what it is. No, I'm sorry, I'm saying this wrong. Give me a second here. Let me unplug that, or let me erase that. I'm making this more complicated than I need to, I'm sorry. My mind got ahead of me and I lost track of what I was doing, so let me back up a little bit. So yes, this is minus F sub 2y because it's going down, and plus F sub 3y. I have no idea why that bothered me when I said that this last time. So now it is going to be minus 150 sine of 90 plus 200 sine of 0, which is 0, is equal to 0. So 150 sine of 90 is 150, but there's a negative in front. So what I have is F sub 1y minus 150 is equal to 0, or another way of saying it is F sub 1y is equal to 150. I just brought it over there, adding the opposite, so it's 150. So I have my x component, I have my y component, and what I'm going to do then is find r. When I have the two components, r is equal to the square root of sigma f sub x squared plus sigma f sub y squared. So it's the square root of 200 squared plus 150 squared which ends up getting me 250 newtons. And then theta is equal to the inverse tangent of the absolute value of r sub y, which is 150. I said r sub y, sigma f sub y, it's the same thing, all over 200. And this time you don't have to just say, oh, I know what it has to be. The math actually works for this one, and it ends up being 36.9 degrees. So my final answer is 250 newtons, 36.9 degrees, and then I'm going to look at the signs. This is positive, so it's northeast. So my guess was right that it was going to be up in this direction, but I don't assume I know anything. So I just make it f sub 1x, f sub 1y. I don't put signs in as though I know. Okay, now there's another one that I can do for you,